Okay, so this is P192 tutorial sheet 4, and we get straight into the first question, which is saying in football association, rules require a football to have maximum volume of 5.8 times 10 to the power minus 3 cubic meters and a maximum pressure of 1.1 times 10 to the power 5 pascals above atmospheric pressure. Okay, so assuming that the thickness of the material used for the ball is negligible, the thickness of the material used for the ball is negligible, and that the air inside the ball is at a temperature of 10 degrees Celsius, take the ideal gas constant to be 8.314 joules per mole per Kelvin. A. Show that the maximum amount of air inside the football is about 0.5 moles. Show that the maximum amount of air inside the football is about 0.5 moles. And question B is saying 1 mole of air has mass 0.029 kilograms. Calculate the maximum mass of air allowed in the football. So which means if we calculate question A, we should be able to use those number of moles that we are going to get in order for us to calculate the answer for question B. So let's just go to our blackboard. We grab some important information. Okay, so they've given us a maximum volume of the football. So the volume they've given us to say it's 5.8 times 10 to the power minus 3 cubic meters, like this. And they've given us the maximum pressure. So pressure is equal to what? Is equal to 1.1 times 10 to the power 5 pascals. So this pressure that they've given us to be 1.1, they've said this is the maximum pressure above the atmospheric pressure. So if this is the P maximum, then what is the atmospheric pressure that we are using? It's 0.1 times 10 to the power 5 pascals, or 1 atm. Okay, the temperature they're giving us to say temperature is 10 degrees Celsius, and the ideal gas constant R is 8.314. I won't put the units. And the molar mass of air they've given us in the question to say it's 0.029 kgs per mole. So this is what they've given us. So what can we do in order for us to start calculating first? Let's convert this temperature that we've been given into Kelvin. And what are we going to do? We're just going to add 273.15. And also we should remember this equation very well. The ideal gas law, say PV is equal to nRT. So this plus 273.15, it will give us how much temperature in Kelvin? 283.15 Kelvin. Okay, so we've converted our temperature to Kelvin so that we are consistent with the units that we're using. Okay, so the total pressure now that we're going to dealing with is the sum of the pressure above the atmospheric pressure and the atmospheric pressure itself. The total pressure that we are going to be using is the pressure above the atmospheric pressure and the atmospheric pressure itself. English, very important. So that means we're adding these two guys, the P maximum and the P atmospheric. We're adding those two as the total pressure that we're going to be dealing with. So the pressure, which is the P total, will be equal to how much? It will be equal to 1.1 times 10 to the power 5 plus 1.0 times 10 to the power 5. Both of these are in Pascals. Okay, so our P total will be equal to how much? It will be equal to 2.1 times 10 to the power 5 Pascals. So this is the pressure or the total pressure that we're dealing with. Okay, so now that we've found the pressure that we are supposed to use, let's now bring in the ideal gas equation. PV is equal to nRT, like that. We want to find the number of moles. That's what question A was asking about. So that means we're dividing both sides by RT, even this side by RT. So that means our number of moles, well, let me put this, okay, our N is equal to what? It is equal to PV over RT. Okay, so our number of moles will be equal to the pressure. We're using the total pressure, so 2.1 times 10 to the power 5, like this, multiplied by the volume. And what is the volume? They've given us to say it's the maximum volume, 5.8 times 10 to the power minus 3 cubic meters, like that, over the R is the ideal gas constant, 8.314 joules per mole per Kelvin, and multiplied by the temperature. And the temperature is 283.15 Kelvin. So this is the temperature that we've calculated. So I haven't included the units of some of these things, like the pressure here, it has pascals, whilst the gas constant there has joules per mole per Kelvin. Okay, so if I multiply the numerators and divide by the denominators, I'm getting my number of moles is equal to 0.517 moles. 0.517 moles. So I've calculated the number of moles using the ideal gas constant. So remember, some of you might thought I was just dreaming when I wrote this as my what? What did I say it was? The molar mass of air. Where did I get it from? We've already been given that in the question. Where is this? It's here to say 1 mole of gas has a mass of 0.2 or 0.29 kilograms. So in order for me to find now question B, what am I going to do? I'm just going to use the mass is equal to number of moles multiplied by what? Multiplied by the molar mass. So this is going to be equal to 0.517 multiplied by the molar mass, which is 0.029 kg per mole. These are moles. Okay, so the mole and mole cancel out. That means I'm having the mass of my gas as 0.015 kilograms. 0.015 kilograms. And that is the end of question 1. Okay, we can move on to question 2, which is saying a white container with volume 9.59 times 10 to the power minus 5 cubic meters contains water vapor at a pressure of 1.75 times 10 to the power 6 pascals and a temperature of 500 degrees Celsius. How many grams of the gas relative or which has a relative mass 0.180 kilograms per mole are in the container? How many grams of the gas relative mass 0.180 kilograms per mole are in the container? Okay, so we go to our blank board. Okay, so this is question 2. Question 2A, and we've been provided with the volume. We're going to say V is equal to 9.59 times 10 to the power 5 cubic meters. Let me check again. The volume is, yes, to the power 5 cubic meters. Then we have the pressure. They've given us to say the pressure is 1.79 times 10 to the power 6 pascals. Okay, R 8.314 joules per mole per Kelvin, and temperature they've given us to say it's 500 degrees Celsius. And if we want to convert this to Kelvin, we just add 273.15 and we have a temperature of 773. Oh yeah, 773.15 Kelvin. Okay, so that is what we have. So what are we going to do in order for us to solve for the mass of the vapor? This is what they're asking for, right? Or how many grams? Yes, which means we're supposed to calculate the mass of the vapor. So let's use the ideal gas equation. We'll say PV is equal to nRT, like this. Then from there, what are we going to do? We make n the subject in the formula, which will be equal to, this is equal to PV over RT. This is P, not R again, sorry. Okay, so, and this is going to be equal to what? The pressure they've already given us, say it's 1.79 times 10 to the power 6 pascals multiplied by the volume, and the volume they've given us to say it's 9.59 times 10 to the power 5 cubic meters. Okay, like that. Then over R, which is 8.314 multiplied by the temperature, which is 773.15 Kelvin. Okay, like that. So if we multiply what's in our numerators and what is in our denominators, this is what we are going to get. Let me multiply on my calculator. Let me plug it in first. Okay, so 1.79 exponential 6 multiplied by 9.59 exponential 5. Okay, I'm getting quite a huge number, but I'll write it. Exponential 6 multiplied by 9.59 exponential 5. Okay, I'm getting a very, very huge number, but I'll write it in case of cases. I'm getting 17, 16, 61, and 7 zeros. 1, 2, 3, 4, 5, 6, 7. So I'm getting this huge number. I'm using a calculator on my phone, so I don't know how to convert this answer into exponents. Okay, then the denominator, we have 773, 73.15 multiplied by 8.314. Okay, so as a denominator, I'm getting 64.27.969.1. Okay, like this. So that means my number of moles will be equal to this. So my N will be equal to, let me divide these now, getting 17, 16, 61, 1, 2, 3, 4, 5, 6, 7, divided by 64, 27.9691. Okay, so I'm getting 26. It's also a huge number. I'm getting the number of moles is equal to 26, 70, 53, 243.92. Okay, so moles. Can I put a mole at the end there? Okay, so I'm getting that as my number of moles, 26, 70, 53, 24, 24, 3. Yes, it's 24, 3. I don't know if I'm making a mistake when punching, but just so far, that is what I have. I don't know if I've plugged the correct things. Okay, this is the number of moles that we are getting. So after we get this number of moles now, what are we going to do? We are going to calculate the mass from the molar mass that we've been given. They've already given us the molar mass, so we're going to say mass is equal to number of moles multiplied by the molar mass. So the mass will be equal to this number that I have here, 26, 70, 53, 24, 3.92 multiplied by the molar mass, which they gave us to be how much in the question. I guess they gave this number. Okay, they gave us to say the relative mass is 0.180 kgs per mole in the container. 0.80, 0.180 kgs per mole. Okay, so I multiply this by 0.18 kgs per mole. So my answer here, I multiply it by 0.18 kgs per mole. Then I'm getting an answer which is equal to mass being equal to 48, 0, 69, 583.9 kilograms. So these are the kilograms, but the question asked us to say we should find the answer in what? How many grams of the gas are in the container? How many grams of the gas are in the container? So what are we going to do here? To convert this kilogram into grams, we're just multiplying it by 1000, but it's already a huge number. It's already a huge number. With 80695 kg, I multiply this by 1000 by 1000 to convert it into grams, and I'm going to get something bigger. Yes, so I'm getting 48 as the mass. So this is the final mass now. 48, 06, 9, 58, 396.4 grams. A very huge number. So 1, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so this will be 4.8 times 10 to the power 10 grams. So the mass of the gas is 4.8 times 10 to the power 10 grams. Okay, so I don't know if I've made any mistakes, but based on what I've calculated, this is what I have. By mistakes, I don't mean mistakes in the formula or anywhere, but just the zeros. There were too many, so if the number is too big, we're prone to errors. But this is what we have. Let's go to question B. Okay, so question B is saying a 6 liters of oxygen gas has a temperature of 30 degrees Celsius and pressure of 2 atm in a closed container. What are the molecules of oxygen gases in the container? What are the molecules of oxygen gases in the container? So we have been given simple and straightforward data. Ready? This gas is 6 liters. 2 atm is the pressure, and the temperature is 30 degrees Celsius. So we convert this temperature to Kelvin. We're going to add 273.15 K, which means we're having 303.15 Kelvin. So this is what I want, or this is what I would love us to know. In order for us to find the number of molecules, we're supposed to use the Avogadro's constant. But before we apply that, we are supposed to find the number of moles. So we're going to use the ideal gas equation to say PV is equal to N R T like this, of which N is equal to PV over R T like this. So the pressure and the volume, we've already been given in atm and liters at the top there. And the temperature, I've converted it into Kelvin. So if you want to find the number of moles and we want to maintain these units that we have here, the liters and the atm without converting them into pascals and cubic meters respectively, the value of R that we're going to use is going to change. Take note of that, please. If we're using this normal one, if we're using pascals and cubic meters, we're using R being equal to 8.314 mole joules per mole per Kelvin. That's the value that we're using. But if we're using the liters and ATM, the value of the R that we're going to use is also going to change. It is going to be equal to what? I'm sure I already know this value of R, but it's equal to 0.0821 liters atm per mole Kelvin. The units are liters atm over mole Kelvin, like this. So this is the one that we are going to use if you're using these units that are here. But if you have the time to convert them into pascals and cubic meters respectively, you should use 8.315. That is a very good trick I've just told you there. A lot of people don't know where to use the this R and this R. People don't know where to apply them. But in this case, since it's either we can convert or we can't, but I'll go with it. Let's just use the same units that we've been provided with here. Okay, so I'm going to say PV N will be equal to the pressure, it's 2 atm multiplied by the volume, which is 6 liters, over R, 0.0821, multiplied by how much? Multiplied by the temperature, which is 303.15 Kelvin like this. And what am I going to have? I have N is equal to 12 over 24. Is it 24? Yes, 24.86. And I have my number of moles being equal to 0.483 like this. Okay, so if that is what I have as my number of moles, Now, what am I going to do? I'm going to convert these moles into molecules directly by using the Avogadro's number. And you know, to say the Avogadro's number is equal to what? Is equal to 6.022 times 10 to the power 23 molecules per mole. Molecules per mole. So if I multiply this number of moles, I'll say my number of molecules will be equal to what? It will be equal to 0.483 multiplied by 6.022 times 10 to the power 23. So the more which is here and the more which is here will cancel out. This more and that more will cancel out. And I'm going to remain with the molecules only. And the final value will be 2.91 times 10 to the power 23 molecules. So that's the number of molecules that I have. If you want, try the other method that I talked about, and it will still give you the same answer. Let's go to the next question, question D, which is saying, determine the volume of 4.42 moles of gases at the standard temperature and the pressure. Determine the volume of 4.42 moles of gases at the standard temperature and the pressure. Okay, so let's go to a blank board here. Okay, so question C is saying we have a gas which is 4.42 moles. Okay, so part C, we have a gas which is 4.42 moles. And our goal is to do what? To determine the volume of this gas at standard temperature and pressure. So what are we supposed to know about standard temperature and pressure? When they say you are performing your or let's say you're performing your calculations at standard temperature and pressure, it means to say 1 mole of a gas. That's what they mean. Remember this statement. 1 mole of a gas of a gas of a gas at STP is equal to what? It occupies 22.4 liters as volume. So which means the volume occupied by 1 mole of a gas at standard temperature and pressure is 22.4 liters. Now that we have that, we can simply calculate the volume from the number of moles that we've been given. Because what are we going to do? We're going to say volume is equal to 4.42 moles multiplied by how much? Multiplied by 22.4 liters per mole. The mole and the mole cancels out. That means we're going to have our volume being equal to how much? Being equal to 98.3 liters, like this. Okay, so our volume will be equal to 98.3 liters, like that. Okay, so today we can or this video will end here. I'll continue recording question 3 only in part 2 of the video. Thank you for attending and have a blessed night.